This is the biggest idea in the history of physics, because it completely changed the way we do physics. It opened up new ways for us to draw conclusions, new ways of thinking about the world, and it helped me get through my physics degree more easily, because that's why we deal with things like frictionless surfaces or spherical bodies. I find it so exciting because for me, this idea sits right at the heart of physics. You could even say that this idea gave birth to modern experimental physics. When talking about great ideas in physics, we usually hear things like conservation of momentum, fundamental forces, entropy, relativity, and many more, because physics wants to describe the world. And those are good descriptions of parts of the world. Those are great ideas that taught us a lot. But the idea I'm referring to is not about a specific description. It's about finding such descriptions in the first place. It's about discovering underlying patterns. So how could you find such a description? You can look at the world as a whole. That would be pretty complex. Or you can look at one special situation and remove as much complexity as possible. That sounds a bit better. And that's already a short version of the greatest idea in the history of physics. The idea that, in idealized situations, physics becomes simple. As Sean Carroll puts it in this brilliant book I finally got myself to read. In physics, we can understand a situation by studying a simplified version of it and treating this simplified version as true. Are you already as excited as I am? No? Well, then let's go over what this idea really means, where it comes from, and why it is so great. Let's talk about the biggest idea in the history of physics, at least in my opinion. Imagine it's the beginning of the 17th century and you want to understand how things fall down. Maybe because you're a curious scientist, or maybe because you drop things all the time. No matter what, you want to understand free fall. That's the situation you're interested in. Up to now, for nearly 2000 years, people thought heavier things fall faster. Because Aristotle said so. And because it feels right. I mean, feathers fall slower than stones. But you're wondering, what if this is just due to air resistance, not free fall? What if it's not the smartest idea to do science by just trusting some guy that died long ago? What if the acceleration of a falling object does not depend on its mass? So, the situation you're interested in is things falling down, and you want to know what role mass plays in it. So, how can you possibly figure it out? You can test it. You can drop different masses and measure how much time they need to reach the ground. That's already pretty groundbreaking, because you let measurements guide you rather than your intuition. But hold on, aren't we forgetting something? In physics, we can understand a situation by studying a simplified version of it, so we wanted to look at a simplified situation. How can we remove complexity here? Well, we are only interested in effects due to gravity and not due to air resistance. So let's simplify things by getting rid of air resistance. You can't get rid of the air, but you can use things that not only have low air resistance, but also pretty much the same air resistance. You can reuse round balls. Now, the influence of air resistance is so small, let's pretend it's not there. And suddenly we've simplified the situation to one at least close enough to the ideal case without air resistance. Unfortunately, it's still the 17th century. Free fall is too fast to precisely measure any differences. Your clocks are just not good enough. But you're a curious scientist. You're not gonna give up. You're gonna make it measurable by slowing the motion down. You roll balls of different masses down inclined planes. If heavier things fall faster, they also roll down faster. Sure, now we also have to deal with friction on the planes. But again, all the balls experience kind of the same friction, and we can minimize it by using smooth planes. So, we removed as much complexity and randomness as possible. And now we are able to only observe effects due to mass. We find that balls of different masses take the same time to roll down, so their motion is independent of their mass. That's fantastic! We already replaced authority and philosophical reasoning with the experiment. But it goes even further. If we use planes with different angles, we find that the motion of a ball depends only on this angle. Steeper angle, faster ball. Same angle, same acceleration, independent of mass. Now, free fall is similar to rolling a ball down a plane perpendicular to the floor. So, same 90-degree angle, same acceleration, independent of mass. That's how Galileo Galilei concluded that all masses would fall in the same way if there were no air resistance. Why is this so great? What's so revolutionary here is the way Galileo came to that conclusion. He minimized unwanted influences like air resistance or friction. Then he pretended those influences were not there at all. Now the influence of air resistance is so small, let's pretend it's not there. Building on this assumption, Galileo established the mathematical connection between acceleration and angle. Since he realized that slowing down the motion doesn't change its nature, he could even extend his conclusions to free fall. So, in order to understand the world, we can study it in a simplified form. We can move from a complex situation to a simpler one by pretending we could remove unwanted influences. Of course, air resistance and friction were still there, yet Galileo could reveal how objects move without them. That's amazing! And it works because physics follows simple mathematical laws. After discovering those laws, we can reintroduce things like air resistance or friction to get an even more realistic picture. Simple mathematical laws can be uncovered through repeated measurements of idealized situations. What a remarkable feature of physics! It emerged in a period we now call the scientific revolution, with Galileo's methods making a significant contribution. During this European scientific revolution, doing physics shifted from ancient Greek traditions to controlled experiments and a mathematical understanding of nature. That's why this period is often called the birth of modern experimental physics. I didn't promise too much, right? I mean, come on. It would be so difficult to do physics if you start from reality in all its complexity. It's so much easier to start from clean limits. It's easier to ask, what happens in the simplest possible case? And how awesome is it that we are so lucky that in physics, answers to this question are usually incredibly helpful. The simplification shows itself in other ways as well. For example, in Newtonian mechanics, when we deal with point objects instead of realistically shaped things. Thanks, Galileo, you made physics so much easier. Thanks to you, physics students only have to calculate this instead of that. So, this could be the greatest idea in the history of physics. In physics, we can understand a situation by studying a simplified version of it and treating it as true. We can move from a complex situation to a simpler one by pretending we could remove unwanted influences. And amazingly, we still get really good insights from that. So, I think that's a pretty good candidate, because it opens up the door to so many other ideas. What idea do you think deserves the title of greatest in the history of physics? Please tell me in the comments. And if you learned something new, please leave me a like and subscribe. Thanks for watching.